So this is our first example. We're going to take the same two curves, a cube root of x curve and an x squared curve, and we're going to find the volume, the picture is drawn there, if we rotate it over the x-axis, and if we rotate it over the y-axis. If you were drawing this as a picture, what you would do is you would reflect this over the x-axis and draw those same points. So if I drew... Did we do the question before this? Yeah, did we not? We didn't finish this one? Okay. Right, we drew the dog dish. I finished it on the video, but I haven't posted it yet. So you can get the answer down for that last one. Now, what's interesting in this one is that you have the integral of cos squared minus sine squared, and we have found that our integrals with cos squared and sine squared almost always use double angle identities. What's really nice about this one is that if you had tried to do the integrals separately, they're both a lot of work. But if you do them together, cos squared minus sine squared is perfectly cos 2x. And that makes your integration easy. Is that enough if I start from there? Yeah, bigger is good because some people and all their best friends lost their glasses. So.
This is my best friend right here. This is what I'm talking about.
As for your mean. I thought beside, there's nobody there. Okay, are we ready for the next one? Almost. Were you done there, Neela? Okay. So, if you're drawing a solid of revolution, and you're reflecting it over the x-axis, what you're going to want to do is, to the best of your ability, reflect this over, right? And redraw the same graphs reflected over. Then take your endpoint, I'll do it in blue here, and draw an oval. And now what's going to happen is this shape is going to get rotated around 360 degrees. Sometimes we color in. All of that and imagine it. And so what happens is if we take a small section, which is labeled right here, I'll color that small section in red. That small section would be equivalently colored in red there, and there would be a washer that if you cut that out, you would get a perfect donut shape or washer shaped item that would get pulled out.
Wow, that drawing's really good.
Oh,
It's really
thank you.
good. I gotta recreate it now.
And if you do a little bit of the shading and you think about it, hopefully you can imagine this shape in your head. You've got sort of a bowl, right? That's been circular bowl with an opening on the inside of it that's kind of got a curve all the way nicely inside. Yeah, if you tilt it on the side, you got a bowl. You can put your cereal in there and have breakfast. And design your new cereal bowls. And we've got our shape. And what we can find out is if we rotate this around the x-axis, what is going to be the volume of this bowl? Now, before we figure that out, we're going to look at doing the same thing if we were reflecting it or rotating it around the y-axis.
I drew the picture. Wait, was I supposed to draw that?
Yeah.
Oh, okay.
So now,
Okay.
we'll go to the y one, about the y-axis. We'll draw this picture again. I'm going to go straight across to here. I'm going to replicate this
Oh, okay.
on this side. Now we're rotating around the y, so now we would have the point -1, 1. And in the same sense, I'm going to take these 2 points, and now, because I'm rotating it around the y, I'd make my oval like that. Take out my crayon. Now my bowl is the right way.
Oh.
That's kind of nice.
You see what's happening?
If we did our washer idea here, they've drawn a section there. This would be equivalent on this side. You would get
Oh, yeah, this
a
looks
washer that way.
Wait, I feel like a tip for next year is to like give them the images.
The helpfulness is if the images were drawn for you.
Yeah, so you could just
Please.
copy what you're
Oh,
drawing.
this is good practice for drawing. Yeah.
How are we even getting that shape? Like, where are we getting that information from?
So we've got two graphs, right? Y equals the cube root of x and y equals x squared. I've drawn those, and where they intersect is at 1, 1.
Oh, and then how do we like flip it?
This one says it's rotated about the y-axis. So that means we've got these little arrow things here. You're going to take this shape and twist it around the y-axis, creating a solid shape with its thickest part sort of there, an opening, make it like a bowl, be a perfect circle bowl.
Well, how do we know it's a bowl? Like, how do we know?
You know it's a bowl because you have to be able to visualize what happens when this part here gets twisted and rotated 360 degrees.
Oh.
And as it gets rotated, it fills in all of that part.
It's like a circle.
It's a 3D bowl because this part, this is our part in 2 dimensions. And then that 2-dimension part, you took it and you dragged it 360 degrees around the y-axis. And as it gets dragged, it fills in the volume of the shaded part, right? The shaded part is an area in 2 dimensions. And that area, as you move it around, becomes a volume. And we can find that volume by adding up all of these little washers that go along. And each of those washers are just one circle minus a smaller circle. And the area of a circle is pi r squared. And since the area between 2 curves is an integral, the area of the volume then just becomes each of these circles added up, which we can do our integration by just integrating pi r squared. So let's look at what that looks like for this. By the way, are these bowls equal, or is
Equal.
one bigger than the other?
Equal.
Okay, we got a very strong equal from the front. Is there anyone who thinks one is bigger?
If it's wrong, it was JC.
What is it? What? Okay, wait, wouldn't there, if we go by the y-axis and then we take the integral there, wouldn't there be like no negatives for the integral? Because if we're going on the x-axis, so there would be a negative component here.
Well, we're adding up all these discs. There's no, when you're finding the area between the two curves, remember that the positives and negatives below and above didn't matter. Because when you subtracted the upper one minus the lower one, you always got a positive value. And since this red length, that is this part here, since that red length is positive, if you then did pi r squared with that length, you would get a positive area for the circle. So it doesn't matter where the object is when it's rotated, the volume will always be positive. But usually what's the case in these rotation ones is they don't give you one curve above and one curve below, because then the volumes would like overlap into each other, and then that's a whole different kind of issue. These questions will almost entirely be something in quadrant 1 where you can rotate it either around the x-axis or around the y-axis. Okay, so I heard no opinions on whether one was bigger or smaller than the other. There was an opinion that there was equals.
I think one's bigger.
You think one's bigger? Which one do you think is bigger? This one or this one?
The one around the x-axis.
Okay. And does nobody think I'm a perfect drawer? That my one around the y was drawn bigger, so it therefore must be bigger? You've learned to not trust any scale drawings anymore in your life?
Yes.
Okay. Well, let's find out.
Especially.
Especially my drawings? Oh, thank you. So what I'm going to do with the washer thing here is I'm going to use the idea of the bigger radius minus the smaller radius. Because we want to do the bigger circle minus the smaller circle. You know the area of a circle is pi r squared. The pi is pulled out because it's a constant in both of them. But here's my bigger radius squared minus my smaller radius squared. And we know that they intersect at 0, 0, and 1, 1. So we're going to go our integral from 0 to 1. My bigger radius, the upper one, was the x to the 1/3. So that gets squared. Minus the smaller one, which was the x squared. It also gets squared. And the nice thing about powers is when you square them, they stay powers. And so our integrals are easy. Just add one to the exponent and divide. And the volume of this bowl is 2/5 pi. Oh, do we have an error here? You see an adding 1 error? No? What happens when you add 1 to 2/3? What do you get? 2/3 plus 3/3, you get 5/3. That. That look better? Oh, and then, but the 5/3 would be there, but then when I divide by 5/3, that was okay, right? Because I would divide by 5/3, which would have a 3/5 out in front. Does it affect our answer? No, our answer is still right, even though we wrote one exponent wrong. Yes.
On a like question, on the test,
Mm-hmm.
would that picture be given to us, or we have to draw it?
Sometimes yes, sometimes no. Sometimes you have to visualize and draw. So I'm trying to give you some helpful techniques for drawing. Right? You've drawn it in 2 dimensions. See how I made the oval? The oval is like a circle turned in 3D to be sideways, becomes an oval.
Okay.
That's not very helpful. You're like, the answer you wanted is, your drawings will always be given
Yeah,
to you.
that's what I
That's what you wanted, I know. A mathematical skill is to visualize something in shapes in space. Okay, here's the second one. Now, since we're integrating and reflecting over the y, we're going from c to d of dy. Again, you'd have your biggest radius squared minus your smaller radius squared. And what we need to do is we need to take each of these equations and write them as x equals. So that first equation, that's y is the cube root of x. If you wanted x equals, you'd have to cube both sides. Agreed? The second one, if you wanted to get x equals, you'd have to square root both sides, which would give you plus or minus the square root of y. But can you see that you only have the positive part, you don't have the negative square root part. So now my x is the square root of y. My y values go from 0 to 1 by coincidence, the same as my x values. Right? So c and d happen to be 0 and 1, the same as a and b. That's not always the case. Depends on where the intersection is. So, my bigger one now, right, is now the one farthest to the right. My biggest radius is the one farthest to the right. That was my x squared, which became my x equals square root of y graph. My smaller one was the y cubed one. We square both. Life is good. Square root went away completely. Add 1 to the exponent and divide. And we got a different answer. Which one was bigger? 5 over 14, or what was the other one, 2/5? Do a comparison of those fractions on your calculator. 2/5 is 0.4, 5 over 14 is 0.357. The first one was bigger. You were correct not to look at the scale of my
Well,
bowl.
it's not the same?
They're not the same.
Why?
It's crazy. They look so nicely symmetrical that it should have been the same. They're close to the same. I like that it bothers you that they're not quite the same. Right?
Like the rotation of the y-axis looks bigger.
Yeah. What the curves of x squared and the cube root of x are slightly different. Does that make sense? Like if it was x squared and the square root of x, to me that feels like there's a lot of symmetry there. I feel like the areas would be identical. But just the fact that the curves are slightly different makes the one area bigger than, or the one volume bigger than the other. Now we're going to do the same thing, but see what happens if we don't go around just the regular x-axis or y-axis. Right? We have, let's say this graph, I'm going to erase things here, and put a line here, and say I want to reflect this thing over that line. It would still make a volume. Can you see the new volume? It would have a hole on the top and the bottom of that one, because there would be a hole here, and then there'd be a hole there, and it would get rotated all the way around. And you'd have all these washers going around each way. That's what we're looking at next when we revolve things parallel to the axis. So find the volume by generating the region bounded by the square root of x from 0 to 4 about the line y equals -3. Ready to draw a picture? There we go. I'm going to make that 4. Here's my square root graph. To make that 4, 2, we are going to take this area, which I'm going to color in nicely in purple. I'm going to take that area, but now I'm going to reflect it. 1, 2, 3. I'm going to reflect it over that line and rotate it about, oh, that's not y equals -. Sorry, let's start again. I drew the wrong line. Can you see yourself ever making that mental math mistake? Y equals lines. Y equals lines are horizontal. Right? So y equals -3 is this line. If I just took that 2D shape and reflected it over, which is kind of exciting because you did that in grade 9 math. This is the last time you took shapes and reflected them over. And you haven't used that topic in grade 9 since in any of your pre-calculus classes. So some people would argue, why are we teaching that in grade 9 if you don't use it? But now we're using it in AP Calculus. So I'm going to go 1, 2, 3, and draw this shape again. Shaded in purple. Can you see where these points would be? Can you see that this one would be at 4, -6? And this one would be at 4, and it's 5 away from here now, so another 5 away would be at 4, -8, and this point would be at 0, -6. And we're going to take that shape and in our rotation, draw an oval here, take these points, draw an oval with them, take these points, draw an oval with them. If I color code this with the crayon so you really can see it, I'm going to shade in this washer in green. And the outside in blue. Can you see a 3D object with a hole all the way through it? There's a cylinder cut all the way through it. Right now, the way that you're looking at it, you're seeing the flat surface that looks like a washer in green, and the blue part is the brown part that goes around it. This would not be a good cereal bowl, because everything you put into it would fall out the bottom. What would this be good for? Looks like a what?
That's a little tiny. Makes it look kind of.
Yeah, like someone who's not very good at cutting.
It looks, to me, it kind of looks like a very claustrophobic dog barking cone,
Yeah,
That's
Right?
avocado.
it's an avocado.
Did you
see the avocado?
Oh, maybe. Okay, so what do? We're still finding circles from 0 to 4. And we still have an outer radius and an inner radius. Now, if I go from 0 to 4, and I take my square root graph like I normally have done, and I add the distance of 3 to it, what I am doing here is basically taking my square root graph and doing a vertical translation 3 units up. If I took my graph and shifted up 3 units up, and I did a rotation around my x-axis, that would be exactly this. And that would give me a full disk and be this full solid that would be involved with that. Figuring that out, oh, sorry, I drew it wrong.
Are you serious?
Well, not super wrong. But the only thing that's wrong in my drawing is you don't have to, it's not actually a claustrophobic dog dish. This would be, the whole thing is rotated around. Wow, maybe not, okay. No, this is still good. Okay, so this,
So there is a hole.
there's a hole. Because if it's bounded,
If you're confused, I'm also confused.
I'm just trying to figure out the wording of this question.
Oh, but like if you don't know what's going on.
It's a good question. The
Daniel,
idea here is, what does this mean? Does it include bounded with the line y equals -3, or are we bounded to the x-axis like normal? That's the question. Find the volume generated by the region bounded by the graph from 0 to 4. About the line, I'm going to say that means this should have been all in purple to begin with. Okay? I'm sorry. So if that was all in purple to begin with and we rotate it around, that would make this a solid disk.
I make it purple right now?
You can make this part all in purple down to there, and this part.
I think I have very good contrasting colors.
So in that here, everything's wrong.
No, everything's right. Except for the coloring.
Everything's gonna be alright, guys.
Everything's gonna be okay.
So it's solid.
My
It's a
drawing's
solid.
But if you can do it,
So this is like the seed in your avocado is still in it.
Okay,
yeah,
good.
but if you can do it correctly with your drawing being wrong, then what's the point of drawing? I feel like that's just more confusing. Like if you
My
can,
drawing is.
like you drew it wrong, but you still did it all correctly, so why do we have to
This
draw
one
it?
is bad.
No, the drawing, the only thing that you can take out of the drawing is the inner circle.
It's just.
But like, how did we actually use the drawing?
How misleading is everything? Shit, every single time. What?
So the drawing helps us see what the overall shape is going to be. Initially, the part of the drawing that we misinterpreted, or I misinterpreted, from the question was that the area is just to the x-axis like normal. But if you're rotating an area from 0 to 4 about a new line, you're doing the area all the way down to that line. Okay?
So like technically you wouldn't need to have drawings. And that's just an additional visual.
Drawing the picture helps you see what you need are figuring out. So it is helpful to draw the picture. Okay?
Do we get-
So then,
Do we ever get marked on front? No.
I don't think they mark you on draft. But I have seen in some other teachers' AP notes, helpful hints for drawing. So it is taught as something that is useful to be able to draw. Now, the solid that we drew can you see that it's identical to the solid by just taking your square root graph and moving it up 3 to begin with? One, two, three. And this is the idea behind, so that one there, where I rotated it about y equals -3, that shape is exactly the same if I took this whole shape and moved it up 3 units. Right? If I took this whole shape and shifted it up 3 units, I would get that shape. Exactly the same. And this graph right here is just my square root graph moved up 3. When we're thinking about figuring out our integral from a to b, it's all pi r squared. Whatever your radius is pi r squared. How do I figure out what this radius is? I figure out that radius. I know from here to here was the square root of x, because that's my normal graph to my x-axis. That was the graph that we were given. And I know from here to here is 3 units. So my radius gets added 3 to it. And then that gets rotated about that line. And so it's just the same as taking my regular square root graph and adding 3 to it, which would be a normal rotation around an axis. So find the volume of the solid of x equals y squared plus 5 from -1 to 3 about the line x equals 3.
By yourself?
Do you want to draw it by yourself?
Yeah, let's try it.
Okay. Teacher, come on now.
Can you what now?
Can we please see the drawing?
Yeah, I'll draw it.
Okay, let's just give it a shot.
Horizontal parabola.
1, 2. Let's just do it as a twist.
Yeah, I think it's drawing sideways. 'Cause
It's
X
drawing
vertical,
sideways?
no?
Mine's like
Yeah,
vertical.
'cause it's X to the Y.
What's an X to the Y? What is that?
Yeah.
Okay. Okay, I have that line too. Let's go.
Let's do the easy parts, right? Let's label -1
Okay.
and 3. How are we doing so far?
Good.
I
That's
didn't get
good.
that far.
And now we gotta draw the hard part. What does x equal y squared plus 5? Right? We want to do it from -1 to 3, so I've got that on my y-axis. I've got the line x equals 3. Now I want to graph x equals y squared plus 5. When y is 0, x is 5. So you have that
Oh,
point.
I got that point.
You got that point? -1 is going to be an important point, right? When y is -1, can you see that x is 6? When y is 3, x is going to be 14.
Oh, wait, I just
That's
plugged
part
it
of
in.
that parabola. I did the whole thing. This will keep going, right? This is the purple part of our graph. Hmm?
Is it this one?
Now, if we reflect that part over to the other side, we'd have a point here, we'd have a point here, and we'd have a point way over there. Not that far, maybe. Oh, it's not to scale. So I'll make it the same not to scale over here. And that would be the other purple part. Make an oval here. Make an oval here. I'm going to pretend this is the top that I can see in green. And this will be the side in purple. I mean in blue. And that's the shape that we have. What does it look like?
So, that's so good.
Again.
A table.
A table.
Oh,
Ooh, it could be a nice like coffee table, side table, right? Fancy restaurant table with like wine glasses. There we go. Some wine glasses. If this is a high school class, so we'll add a soda pop instead. There we go. We got a fancy restaurant table as a drawing. And you want to make this restaurant table out of quality recycled plastic. So you have to order some recycled plastic, melt it down, and put it into your table. How much recycled plastic do you need to order? We need to find out the volume. So what would we have to do? Normally, you would go all the way to your y-axis when rotating. But now this time we have to shift, our y-axis has been shifted 3 to the right. So if we want to bring it back, we would have to subtract 3 to bring it back. like terms, integrate as per normal. And whatever units you were having, you have to buy 52 pi over 3 units cubed of plastic to make this table for your fancy high-end restaurant. I've seen park benches with like completely recycled solid plastic stuff. They're kind of eclectic. I don't know if I love the look of like 40 different colors of plastic mixed in fire.
I have a question. How do we know where like the graph is starting?
How do we know where the graph is starting, as in which graph? The blue graph, that's the parabola?
Yeah, how do you know where to put that?
Well, I did a little bit of table of values. Oops. And horizontal parabolas really are the same as vertical parabolas, just horizontal. You just have to flip your axes. So here is the equivalent thinking of, if you had y equals x squared plus 5, you see that you'd have a parabola moved up 5 units. We have x equals y squared plus 5, that parabola is sideways, moved to the right 5 units.
Oh, okay.
It still has all the same properties of regular parabolas, that you know that over 1, down 1, over 1, down 3. Now it's down 1, over 1, down 1, over 3.
Oh, and then you just flipped it.
It's just a sideways
on the other
parabola.
side.
And I flipped it on the other side, exactly the same distance from the red line. So this distance was 2, so I flipped it 2. This distance was 3, so I flipped it 3.
I get it.
You got it?
Yeah.
Awesome.
Okay, here we go.
All right, we should give you the option for your second credit. You can either get an advanced math credit or an Art 40 credit for this course.
I think the R40.
You take the Art 40?
Yeah.
Awesome.
It's muted. Wait, is it muted right now?
Oh, it's been muted. Okay. It's back on. We'll miss the Art 40 credit option on the video. Thank you for noticing. Hopefully it hasn't been like that for too long.
Okay, you can't go back and watch
Yeah.
the video now. Really good.
This picture's drawn for you. You don't have to draw it.
Good. Look at it.
Does it look like it would be a little
It's like
complicated?
winds. It's like jets. Like what's going on? It does?
So now we have an area between two curves, and now we're taking that area between the two curves and rotating it around a new line. So there's my area between the two curves. In the first picture, just shows the little section, and it shows a little part. Now if we took that little part and rotated it around the y equals -5, you'd make a nice washer. And if you added all those washers up, you would get, this looks like the dog barking cone. But perspective-wise, that's a very big head. I think the length of the head of the dog would go past this, not a good design. Sort of like a little crown for the dog, but it will still bite you, and you will die. Not great that way. So what do we have to do? We have to find our volume, which is our bigger radius minus our smaller radius. Our bigger radius is the red line. That's our 2x line. And the 2x would just get us back to the x-axis. We would have to add another 5 to get to y equals -5. Our smaller one is the x squared graph, and we would also have to add 5 to that to get to that -5 line that we're rotating around. even though the y is at -5, what we're figuring out is bigger radius minus smaller radius. And up to here, up to your x-axis, this is 2x and this is x squared. To make the radius, you have to add 5 to it because it gets bigger. You would subtract 5 if your radius was smaller than normal. So anytime if I had decided to rotate something above the x-axis, so now your radius is smaller than it used to be, then you would subtract. So when did we subtract? We subtracted in this last example, right? We subtracted the 3 because normally you would go all the way to your y-axis, but now you're going 3 less than normal. Expand this, combine your like terms, and now life is easy. And this is where we'll stop for today. With the killer dog. We should have stopped at the fancy restaurant. It would have been less morbid.